Hi there, I'm Robin from Delft University of Technology, and I will present to you our recent work for the Accelerated Big Data Systems Research Group. Before I introduce our solution, I'd like to quickly explain the context of the problem we are addressing. Big data application developers of course want to leverage the benefits of memory as much as possible, but often available memory within compute nodes is limited even if data center as a whole is ample. This obviously clashes with the continuing trend of the increasingly large data volumes that are accessible to us. In order to overcome local memory limitations, big data frameworks like Apache Spark allow the developer to divide their dataset into partitions and to distribute these partitions across compute nodes. The compute nodes can then intercommunicate over the local network whenever necessary. This works great while mostly operating on local data. However, quite often we need to combine data from multiple partitions. The type of operation which requires input from more than one data partition to complete is called a wide dependency operation. The diagram aims to explain this further. Imagine the blocks are data partitions, and in order to calculate the green block, we need input from all the blocks that have arrows pointing towards it. Examples of such operations in Apache Spark are the group by and certain join operations, which are notoriously expensive. The problem with wide dependency operations arises when operating on distributed datasets, as accessing remote partitions incurs a latency penalty for having to cross the local network. Moreover, shuffling data across the network might require a node to expel data from their local memory, degrading performance further. Recently, the Thymesis Flow memory disaggregation framework was introduced, which allows compute nodes to directly access an adjacent node's memory regions at minimal cost. This is done by exposing a disaggregated memory region, which is serviced by the Thymesis Flow hardware and software interface to guarantee consistency and performance. If we connect two nodes both ways, memory disaggregation can function similarly to shared memory across nodes. This could help solve our wide dependency problem by allowing the combined processing power to act on the entire data set in memory. However, in Thymesis Flow, some cache coherency intricacies prevent us from bluntly treating it like shared memory, the details of which can be found in our paper. With some extra work though, we can still use the technology to our advantage. For this, we build on the Plasma Object Store, which is part of the Apache Arrow framework. It provides a shared memory service for applications to store and retrieve immutable data objects. By providing a standardized format and minimal serialization overhead, it delivers very high performance. It works as follows. Applications can create objects with identifiers in the Plasma Store and commit their data to shared memory. After this, other applications can request a buffer with the object identifier from the Plasma Store to access the memory location of the immutable data. By combining Thymesis Flow and the Plasma Store, we aim to provide a solution to improve performance mainly for wide dependency operations, but not limited to them. For this, we integrated memory disaggregation into the Plasma Store such that clients can access objects on remote compute nodes. We use the immutability of the data objects to our advantage to ensure that cache coherency issues do not arise. In this, we provide a framework that we hypothesize can provide improved performance for wide dependency operations with simple programming models. In order to integrate these technologies, we modified Plasma to allocate objects in disaggregated memory and added an RPC interface for orchestrating existing objects between remote Plasma stores. For example, when creating an object, the Plasma Store makes an RPC request to ensure uniqueness of the object identifier across the distributed system, as otherwise applications might not be able to access all objects. Creating and retrieving local objects then works the same as it did before. However, the behavior is different when a process requests a remote object. The local plasma store will receive the request and will not recognize the object identifier. The local plasma store will then relay the request to the remote plasma store. If the remote plasma store recognizes the object, it will return a buffer with the object to the local plasma store. The latter then forwards this buffer to the requesting process, which can then retrieve the object data from disaggregated memory and continue its way. To prove the system, we set up micro benchmarks to measure the full round-trip latency of fetching an object from local and remote disaggregated memory separately. These measurements include both access latency and data throughput. The benchmarks vary the sizes of the fetched objects across 6 orders of magnitude to capture any potential differences. We can then compare local to remote performance over the different benchmarks to identify trends. The results are expressed as throughput and shown in the diagram here. The data for the smaller object sizes shows larger variability and appears to be influenced by boilerplate code significantly more than benchmarks 4 to 6. For the latter, the measurements converge neatly, which is indicative of reaching memory bandwidth limitations. The measurements demonstrate that remote throughput is close to local across the board, which is a promising result. Performance also appears competitive with existing state-of-the-art RDMA technologies. Some main hypothesized improvements to the system could be provided by a more intricate communication interface between remote plasma stores, improved memory allocation, and advances in underlying memory disaggregation technology, like memory inception as announced in Power 10. With that, we conclude that we have successfully demonstrated our novel memory disaggregated object store framework for big data analytics purposes. Furthermore, the benchmarks indicate that performance for remote object fetching is close to native, demonstrating the proof of work for our framework. And lastly, the paper provides a stepping stone for future research to improve performance of the framework to integrate it into existing big data workflows. Our main contributions in this paper are the proposal of the framework, the benchmark results, and extensive considerations and recommendations for future work. Additionally, the work is open source and I invite everyone to contribute. With that, I would like to thank you for your attention.